Greetings, chemists. Today we're going to be going over different types of chemical bonds and bulk properties of those types of materials. So, we're going to start with our good friend, the periodic table. And I'm going to remind you of something we talked about in a previous lecture, which was that the atoms at the top right of the periodic table, with the exclusion of the noble gases, tend to be higher in electronegativity, with fluorine being the most electronegative element on the periodic table, whereas the atoms at the bottom left of the periodic table are the weaker atoms, are the lower electronegative atoms. And in this context, electronegativity just means if you have it, you steal other people's electrons, or you have a greater ability to steal other people's electrons. And if you don't have it, you get stolen from quite a lot. And don't forget that our purpose, you could say the end goal of every atom, as if they were individuals or something, but they become stable when they are like noble gases, when they have a fully filled energy level. So it's actually beneficial for the stuff on the right side, the atoms on the right-hand side, to steal electrons because it gets them closer to that fully filled orbital. And it's actually beneficial for the atoms on the left side to give away their electrons because then they get closer to zero. And zero, let's think about this, if potassium lost its outer electron, one before potassium is argon, he's still got a noble gas configuration. Okay, so that's where we're starting from. So bonding types are largely a function of electronegativity. All right. Let me start with some atoms that are extremely different in electronegativity. And I'll bring the table back. You couldn't get two atoms more different, hardly, than fluorine and cesium. Those are about the two most different atoms on the table. So if you had fluorine, the most electronegative, and cesium, one of the least electronegative, okay? And I'm going to put them next to each other. And let's see what that does. Okay, here's fluorine atom. Super strong. Here's a cesium atom. Now, if I draw fluorine, one of the reasons he's super strong is he only has two energy levels, and he's filled up 1, 2 electrons on the inner level, and 1, 2, 3, 4, 5, 6, 7 electrons on the outer energy level. Now, cesium, one of the reasons he's so weak is he's on the 6th row, right? I'm not going to bother drawing all of his electrons, but 1, 2, 3, 4, 5, 6. Look at that. All those shielding layers and one little electron on the outside. Now, he has a bunch of protons, this cesium atom. I won't draw them all, but they're in there. He has 55 of them, and fluorine only has 9 protons. But look at how many layers of shielding are blocking those cesium protons. So that cesium can't really pull very hard on anything else. He can't pull on his own electrons. He can't pull on fluorine's electrons. So he's not going to be stealing from fluorine. Now, fluorine, by contrast, his 9 protons have almost no layers blocking them. So he can hold on to his own stuff really well, and he can really hold on to cesium's much stronger. So he can actually pull on cesium's electron harder than cesium can pull back. Okay, what happens then? Fluorine is strong enough that he can rip that electron off of the cesium atom and take it. Now, I didn't draw these inner levels on cesium. They were all full. So picture all of those inner levels being full of electrons. But he only had the 1 electron on the outer level. So look what happened. His outer level goes away. And what's left is this inner level that was already full. So now his actual outer level is a fully filled orbital because we got rid of the non-filled orbital that was surrounding it. Fluorine's outer level is now completely full as well. This makes them both stable. They are not likely to react anymore. And it also makes them both ions. Now, fluorine gained a negative charge, so he would now be the fluoride ion. Cesium is left with a positive charge, so he is now a +1 ion. Okay? That is an ionic interaction. By definition, we created ions. Think about what we created. A positive and a negative particle. Well, a positive and a negative particle, you know what happens. Opposites attract. They are going to try to stick together. And so what you will get is a cesium atom stuck right up next to a fluorine atom. And that's what happens. So you get cesium fluoride. Now, the positive and the negative will actually cancel out overall, right? He will hold the positive on his atom. He will hold the negative on his atom. But together, as a pair, they are going to have a neutral charge. So this is not a charged species individually or in terms of pairs, but it is. But each individual ion happens to have its own localized charge. Okay? That's an ionic interaction, and we call it an ionic bond. And in this case, the bond is that they're like, you can think of it similar to the way magnets attract. Magnets do something slightly different, but that sort of at a distance pull is what's happening here between the positive and negative charge. We would call it the electrostatic force. Now, if you had a whole sample of fluorine gas, let's say these are all fluorine molecules, and you pour them or blow them because this gas over a big block of cesium particles, so here's my fluorines, and here's my cesiums, and this all goes and interacts, and each fluorine steals an electron from that cesium, well, what you're going to get is several negative fluorines and several positive cesiums. So if the cesium is the positive, a lot of the fluorines will stick to him like this. And if the fluorine is negative, a lot of the cesiums will stick to him like this. And you get this like lattice. You get this interwoven, interconnected ionic block of atoms that just keeps growing. And eventually it forms a crystal. Okay? That is an ionic interaction. It is a transfer. So I'll say ionic bond is the type that we call this. It is a transfer of electrons. It forms a crystal structure, generally. And it's one of the stronger interactions out there. Although we'll talk about what that means in a little bit. Okay? That is the way. Now, to get an ionic bond, I should add on to that. The reason it worked is that we took something really strong and something really weak, and we put them together. In general, how strong do you have to be, right? What difference, right? What's the difference between like fluorine is obviously the maximum and cesium is like almost the minimum. Would fluorine do it with magnesium? Would fluorine do it with nitrogen or oxygen? And not all of the elements will be different enough in electronegativity for that to matter. So on the periodic table, we look at these green guys here. These elements that are in green are the dividing line. If we take elements from this region, these are the nonmetals, they are strongly electronegative. Again, ignore the noble gases. Sorry, my hand is covering it. So if we ignore the noble gases, everything else, basically the stuff in yellow, is strong enough to take electrons. If you're not on the green side, if you're somewhere over here, these are the metals, and metals tend to be very weak. They're on the left side. So metals can be stolen from. So to get an ionic bond, you need a non-metal versus a metal. Okay? Hydrogen is a little bit of an exception. Hydrogen shows up on the left-hand side, but you see how they colored him yellow? Hydrogen tends to act more like a non-metal than it tends to act like a metal. Okay? At least at standard pressure, at room temperature and pressure. If you go to the surface of the sun, hydrogen actually functions much more like a metal than like a non-metal, but you're not there. So that's how we get ionic bonds. So let me write that in here. An ionic bond is metal plus non-metal. What about the green guys? The green guys don't tend to form ionic bonds either way. They're a little too weak to steal from the metals, and they're a little too strong to be stolen from by the non-metals. So we'll put them in their own class for now. And we'll move on. So so that's with a weak guy and a strong guy. Let's go to the next one, which is what we would call let's take the similar example, but we'll take fluorine and another fluorine atom. Let's take two fluorine atoms. Okay, so here's a fluorine atom with 2 electrons in the inner, 1, 2, 3, 4, 5, 6, 7 on the outer. And let's take this fluorine atom, 2 on the inner, 1, 2, 3, 4, 5, 6, 7 on the outer. Okay? Now, they are both very, 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 very strong. In fact, fluorine is the most electronegative ever on the periodic table. But it's not like this atom is stronger than this one. They are identical. They have the same electronegativity. So he can pull on his electron very strongly, and he can pull on his electron very strongly, but they can't win. They pull the same strength. And so in this tug of war that's going on over these electrons, right, this guy is trying to grab onto his electron, this guy's trying to grab onto his electron, and they just get stuck. And they can't leave each other. Now, if we were to push them very close together, what you would see is something like this. See if I can draw it. Fluorine here. You would see their orbitals start to overlap. And indeed, they do pull each other very close. And for that brief moment, not brief, for the length of time at which they both overlap, that's the electron from this fluorine and that's the electron from this fluorine, but they're almost shared. They're almost in a shared space in between them. And they're stuck in this tether, this tug of war, so they can't get away from each other. But they have also sort of satisfied their octet. Remember before, when there was stealing happening, the whole goal was for fluorine's outer shell to be filled and for cesium's outer shell to be filled. Well, you could almost imagine that as long as they don't move away from each other, these two fluorines have filled each other's outer shells. But they only stay that way as long as they're connected. If they were to separate, then one of them would have to take an electron with them, or two, or something, and then they would not be both stable outer shells. So they achieve a stable octet configuration only by staying in close proximity to each other where their orbitals overlap and where those electrons more or less get shared by both atoms. So what we call with this is covalent bonding. And what we see is not a transfer of electrons like in ionic bonding, but we see a sharing of electrons. We see that in this case, it didn't happen because one was strong and one was weak. It came because they were both strong, or because they were both at the upper right of the periodic table. That's the non-metals. So this is two or more non-metals make up a covalent bond because they're both strong. And you don't tend to get a repeating crystal structure like you do with cesium fluoride. With cesium fluoride, a positive is going to attract as many of the negatives as it can. A negative is going to attract as many of the positives as they can. But these were just individual ions that were freely floating around and are just now going to stick together like a big cluster of magnets. Here, this fluorine and this fluorine are stuck to each other. But if we had two more fluorines get together, I won't draw the electrons. There's these two are connected and these two are connected, but there's nothing connecting these two. This molecule on top with this molecule on bottom. So there are a bunch of free floating atoms. So these are unique molecules not connected in a lattice, okay? Which is much different than with the ionic crystal lattice, which is very highly correlated and connected. Okay, so we've done so far strong with weak, that was ionic. We've done strong with strong, that was covalent. What happens when you get two weak guys together? Well, the weak side of the periodic table, remember, not metals over here, yes metals over here. All of these, there's a big section. Most of the materials or atoms in this world come from the metals side. Well, metals are weak and weak. What if you put two metals together? So with metals, there's a couple of things going on. Let's take two aluminum atoms. Aluminum has 3 energy levels, like this. And he fills the first 2. And then has 3 electrons on the outer edge. Now, the outer shell for aluminum can hold 5 more. It can hold a total of 8, right? It could have 8 here. So there are 5 empty spots in his outer orbital, and there are 5 empty spots in his outer orbital. And this is tough, because remember, they're trying to get to 8. He doesn't even have 8 to share with him. Plus, they're not very strong, right? With fluorine, it kind of worked because fluorine was strong enough to hold on to the other fluorine atom's electron. It was like a really strong bond. Where this is 2 weak guys getting together. They can't really force themselves together like that. But what if we had a 3rd aluminum and a 4th aluminum? And again, I will draw out all the inner electrons together like this. Okay, their outer electrons can sort of overlap, but it would take all of them. Now, fortunately, aluminum has a lot of empty space, right? There's a lot of empty orbital space. And so what happens is, there's the theory with metallic bonding is that this guy's electron has the ability, he can't hold on to it very strongly, and neither can any of the rest of them, so these outer electrons will generally migrate through all of the other atoms in the sample, and they can freely flow. We think of it as a big sea of electrons. Everybody, they're not localized on one aluminum atom. They could be moving here and here and here and here and here, and in that way, all of the atoms get a little bit of everybody else's electrons, especially because they can't hold on to them very, very strongly in the first place. That's the idea behind a metallic bond. So a sheet of aluminum, that's what's holding all the or not holding all the electrons in place, but they're all sort of migrating. You can also do things like, well, we'll get into that in a different video. This leads to certain properties. Okay, so for the metallic bond, this is a sea of electrons. It's shared among multiple atoms. So what do we make of this? Remember, we talked about how hard it was to boil something, or what it took to boil something or melt something, okay? When you go from a solid to a liquid to a gas, what you're doing is you're putting in enough energy to separate those particles from each other, to either get them to move around or to get them to bounce away from each other and fly through the air. That's what boiling would be. Ionic bonding has very high melting and boiling points. You can imagine the reason for this. Look at all those little magnetic attractions, right? The positives and the negatives. They are stuck to each other. If you wanted to heat them up to the point where they could flow, where they could have enough motion to move around, you would have to overcome all of that force that's holding them in place. And it's a strong force holding them in place. That's a very high melting point. If you then wanted to heat them to the point where they could fly away from each other, you have to go even higher because there's still a very strong force holding them together, even when they're moving. All right. So it takes a lot of energy to overcome that force that's holding them into that very rigid crystal lattice. Some of the things that ionic bonds tend to do, if you were ever to melt them, liquid, right, or molten. Let me make sure I mention that. Molten also means liquid. Molten, we would call this a salt. This crystal is a salt crystal. That's the name given to ionic crystals. That's where the term salt comes from, is an ionic compound. Molten salts conduct electricity. Now, electricity is just a flow of charge, and every single one of those fluorines is -1, and every single one of those cesiums is -1. So once you break them free of their spot on the crystal lattice and give them enough energy to flow by melting them, if you were to put an electric current through them or try to apply an electric field across them, you would get an electric current because they are themselves ions. They can flow. When they're solid, they don't. Solid salt particles can't conduct electricity because they're fixed in place, right? And you have to be able to move to conduct electric current. This crystal, because it's a crystal, it's very brittle. If you drop it, it would shatter. There's not a lot of room for them to move. And so putting a big enough force on them just break them into pieces. But they can fracture, right? They can split because they already were individual atoms. It just takes enough force. Think about separating two magnets. You could pull two magnets apart, right? They're not like glued together. They're just attracted to each other. Okay. Now let's compare that with a covalent bond. Covalent bonds are not charged at all. They weren't positives and negatives. So if they start to flow, which they can, right? These atoms were not attracted to, the molecules were not attracted to each other. The atoms were just bonded with this like tether arrangement, right? You can think about a bungee cord. So these guys do not conduct electricity under any circumstances, really. I don't want to say any circumstances, but whether they're solid, liquid, or gas has very little to do with whether or not they conduct. So do not conduct electricity. Let's think about whether it's easy to boil or not. Fluorine is actually a gas at room temperature. It's already a gas. It's already been boiled. It doesn't take hardly any energy at all. And you can think about why. This is its own molecule. This is its own molecule. It's shielded from each other. There's no positive, negative force holding them together. There's nothing. We'll find out in other chapters why, but there's not hardly any attractive force at all. So it doesn't take much energy to get them to just float away from each other, which is what gases do. In fact, the energy associated with room temperature is more than enough. Not all covalent molecules, like fluorine, start as gases. There are covalents that are solid and liquid at room temperature, both. But compared to this, so if you look at ionic crystals melt at temperatures of like 2,000, 3,000 Fahrenheit or Celsius, whereas this stuff is going to melt at like 100 or 200, depending. Okay, so relatively low melting and boiling point. Unlike these, they don't tend to form crystals. Some of these will be solids and some will be gases. Sugar is my example that I use. Sugar is a covalent molecule. Sugar is this C6H12O6. Carbon, hydrogen, oxygen, all of those things are not metals, right? So non-metals was our rule for covalent bonding. If you drop a salt crystal, it shatters. If you took a sugar molecule. Think of like gummy candy, like a gummy bear. A gummy bear is a bunch of sugar and some other things. And you squeeze it, it squishes. Okay, so you can make sugar crystals if you're careful, but a lot of sugar gets very squishy when you put pressure on it. And other covalent molecules tend to be less crystally and more squishy in turn, okay? So more squishy. Okay, what about metals? Well, the easy thing to talk about is their electrons. Their electrons, like we said, are not stuck to one individual atom. They can freely move and do freely move as this sea of electrons through any of the atoms. So if you wanted to try to get them to conduct electricity, it's very easy because their electrons are already so mobile and there's all so much space for them to go. And you don't even have to melt them for that to happen. They can be in the solid form where the atoms are not really moving and the electrons can still be mobile. So this is, metals do conduct electricity in solid or liquid form. Not necessarily in gas form. They get to there. What about boiling versus melting? Well, what tends to happen, so before we start talking about that, having this free-flowing sea of electrons does something very interesting, which is that if I were to take these and squish them together, because the electrons can get out of the way, that actually allows this to be somewhat bendy. So if you've ever taken a metal and tried to bend it, it bends pretty easily, and the reason is that the electrons allow these atoms to get pushed closer together or pulled farther apart. There is some flex in the crystal, in the structure. It's not as hard as a crystal or as rigidly in place as a crystal. If you compare it to these guys are slammed up against each other the entire time, like magnets, okay? There's no space in between. But there's some space here in a metal lattice where you can bend it, you can draw it into a wire. So what we say is metals are malleable. And malleable means you can kind of rearrange them into different shapes. You can bend, you can draw them into a wire. You can't really make a crystal into a wire. It would shatter if you tried to stretch it into a wire. Okay? There's some flex to them, and it has to do with that sea of electrons. So by that token, if you wanted to try and melt a metal, they can melt at lower temperatures than ionic, although they still melt at well, it depends. So, for instance, gallium. There's a metal called gallium that if you put it in your hand, it will just melt, right? It melts at like hand temperature, essentially. So, lower melting point. And the reason it can do that is that just like the electrons are free to move around, well, if the electrons aren't localized to one atom and they're not tethering the atoms in place, then those atoms can get to a point where they're free to move around each other and still get the benefit of having all of the electrons of their neighbors, right? That sea of electrons is what gets them closer to their octet. However, compare that to try to boil them. If you tried to boil them, you would actually be pushing them very far away from each other to the point where their electrons no longer overlapped. And that overlapping sea of electrons actually is important to reaching their octet. So it's much, 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 much harder to boil a metal than it is to melt a metal. So they can have higher melting points, they can have lower melting points, but they have high boiling points. Because at that point, you are removing the individual nuclei from all of the supporting electrons that would be completing their outer shells. And that's less stable. Okay? All right, those are the types of bonding and more importantly, the explanations for why that type of bonding explains the way those chemicals behave at a macroscopic level.